So from Wikipedia, the renewable energy is renewable resources, something like sunlight, wind, rain, and tide, and waves, and geosummer. Okay, among them, ocean renewable energy can cover sun and wind and tide and waves and also geosummer heat too. So only rain may be not easy to utilize it on ocean. It can, there is rain, but the area should be big to collect rain to be used. So that is not easy in ocean engineering. And the renewable energy provides energy in 4 areas, something like electricity is the most important. And then another one is heating and cooling. And third one is transportation. And the final one is energy services. Local, rural, local, off-grid. Smart. There is a grid. All the electricities are connected through the grid. Nowadays, they are saying about smart grid. But this one is off-grid. Something like a small island. For Koreans, it can be a Dokdo Island. And there are so many small islands where the land side electricity cables is not provided yet. Then they should provide their own self-sustaining energy sources. In that case, you use renewable energy too. Right, in graphical term, the sun is the main source of energy of the whole Earth. Right? So you see that there is a percentage of sun energy going to direct conversion to heat. That is about 50%, 47%. And then right-hand side, solar radiation, short wave radiation, and hydrological cycle is 23%. Short wave radiation is 30%. The others are very small. But there still has hydroelectric power, ocean tide, and convection. Wind energy. We are concentrating on wind energy for the moment. Wind resources, the sun radiates amount is big megawatt hours of energy to the Earth per hour, right? And the wind is a byproduct of solar energy because of the heating of the Earth's surface and cooling of air. Their circulation is started. Only 2% of sun's energy is converted into wind energy. But still it's big energy. The whole energy of the wind of the Earth is only 2% of solar energy. Now, the solar power and wind power and geosummer and global consumption is converted into shown as small boxes. So you see that the right-hand side, the global consumption is only 15 terawatt, but whole wind of the Earth is much bigger. So theoretically, if we convert some of that wind energy into human electricity, then we can have enough wind, right? But it's not easy. So the size of energy is shown here. And resources around the Korean Peninsula is shown here. as something like a weather map. Okay. And right-hand side and above, see that the red color is the high wind area. So that you see that around the Jeju Island in south of peninsula and east south corner of the Korean peninsula near Busan or Ulsan is more higher wind energy. Okay? So that is the place we can do a wind power system. And from bottom right hand side, you can see that there is already installed wind power systems. So you can see that most of them are in land-based currently from this picture, but now they are moving out to the ocean because of the land is not, land resource is scarce. So why wind power? Comparing to the solar cell or other wave energy and tidal energy, left hand side you see that advantage, the lowest priced. So it is economical comparing among renewable energies. Wind power is economical. Price is low. For the technology, today's technology level. In the future, probably solar energy can be solar cell, solar electricity can be better, but depending on the technology development. But currently, wind power is the cheapest or economical. And trend of wind turbine, lightweight, low solidity and flexibility, but as I pointed out in red color, the diameter is increasing so that the tip speed is big. Right? See, if you imagine the blade size of diameter 100 meter, the tip speed RPM is a rotational speed, angular speed should be same in the hub side and root side and tip side. But linear speed is very big on the tip side. Right? So sometimes when the diameter is more than 100 meter, the tip speed can be supersonic. Supersonic means faster than speed of sound. Okay, so that can be a very high speed. Right? And passive load relief, that is, you can see in the later stage that twist and bending is available by nature or by material. So when the wind speed is fluctuating and when there is a gust is coming, high speed wind is coming suddenly, then the wind blade is change their shape so that the angle of attack is smaller than before. We call this is a passive load relief of the bending stress through twist and flap coupling by using material and geometry. Okay. So we call this is a BTC blade of wind power. BTC is a bend twist coupled wind power blade. And skew system. When we study on submarines, the Navy submarine, not commercial, Navy submarine has a specialized shape of propeller we call the skew propeller. Why they use that kind of skew propeller? To minimize the noise coming from propeller. Right? That is the same idea when we can use in reverse way, the passive load relief way, so that they generate less bending or stress. Okay, and stability is also important. Not only load. Load means stress. Right? Stability is a different kind of a way of structural stability, also electrical stability too. In right-hand side, you see that the yearly change in Europe and North America and Asia, the speed of increase is highest in Asian countries, especially in China. And bottom right, there is a Young's modulus, and in vertical axis, and horizontal axis shows density. There is a metal, ceramic, polymer, wood, and foams and rubbers. But in the middle, there is a dark area. So we see that there is a material that can be used for the wind power system, blade. FRP is the main material for the wind blade manufacturing. Here is how the wind turbine is working. Wind turbine is trying to convert the kinetic energy. Kinetic energy is coming from wind into mechanical power, right? And then the mechanical power converts that into the electricity. The generator inside the wind power system can convert this mechanical power into electricity. So in left-hand side, the bottom, there is a picture. Inflow wind is starting, number one, that rotate the blade. Inflow wind activates a rotor. Rotor is rotating by using a blade, angular vortex. And then what is C? C is the rotor blade spin, the main shaft. The C is the shaft. And D is the gearbox. They usually increase the RPM by using gearbox. And then G is the real generator, which can generate the electricity. After electricity is generated by generator, then the electricity can be collected through the cable up to the relay tower. And the relay tower sends the electricity to home, such as my home in city something. Right? That is the way the wind turbine is working. Now, the wind power system, it has two different types. One is a vertical axis, the other one is horizontal axis. So right-hand side, you see that the horizontal axis wind turbine. Here, the axis of generator and brake and turbine, the rotating axis is horizontal to the Earth's surface. Okay? And that is a typical shape of we are accustomed to. And left-hand side, the rotational axis is vertical to the Earth's surface. And this is not popular in real world, right? But there is also ideas we can use for this vertical axis. Because why? Because the size of wind power is increasing up to 20 megawatt. The size of the blade is increasing up to more than 100 meters. And then the other things are more bigger and heavier. So the tower of the horizontal axis wind turbine, weight of tower, size of the tower, and including blade is increasing bigger and bigger. So that you need to have a very strong and big size of tower in horizontal axis. But for the vertical axis in the left-hand side, the weight of the whole wind power system is supported by the bottom of the gearbox there, lower hub there, and rotor is rotational axis is vertical, so it's more easier to design the structural part of this type, even though the efficiency of generating electricity is a little bit lower in vertical axis type. But anyway, there can be a technological development in the future, so that vertical axis has a structural advantage. So in the future, it can revive again. Right? So we should see the future technology. All right, any question up to here? No? We can move on to, so we already see this one, right? And also I put your exam, in the midterm exam, I did some questions on that. So the size of 10 megawatt wind power system in 2010 year, the diameter is 180 meter, right? Very big, right? It can be 20 floors building, right? 150, 180 meter can be, right? No, more than 20, right? 100 is about 20, right? So it can be 35 or 6 floors. Ooh, very high, right? 36. We cannot. Is there any building in Daejeon area which is higher than 36? Probably in, yeah, several in Daejeon area, right? So anyway, it's a big wind power. And here is the nuclear power plant developed by Korea. KHNP is a short name of Korea Hydraulic Nuclear Power Plant Company. And they have their own design type of 1400 type reactor. Right? So reactor is in the center part with the circular dome, spherical dome, cylindrical dome. The others are the other facilities, something like a generator or turbine or other facilities. So this one, 1400 means 1400 megawatt. 1400 megawatt of this nuclear power plant. It's a big one. So electricity of nuclear power plant generation can be 1400 megawatt. Comparing to this one is saying that 10 megawatt, right? 10 megawatt. So how many of them can replace this nuclear power plant? Is 140 of this 10 megawatt wind power system. So you can say wind farm. There are a lot of wind generating facilities as a farm. Then you can replace one of these nuclear power plant. There are more detailed ones, something like NREL. NREL is a United States research laboratory called National Renewable Energy Laboratory, and National R Renewable E Energy L Laboratory. And they have a very famous 5 megawatt design and testing and experiment. And DTU is a Denmark Technical University. They developed a 10 megawatt design and also testing too. And this one is a PhD thesis work. So it only has a conceptual design there. Where he proposed a 20 megawatt wind power system, and rotor diameter is about 300 meters. Ooh. And Saturn V is the biggest rocket launched from the United States. This is only 110 meters. So you can imagine the size comparison of this. And power range, you can remind that horsepower is about 746 watt. Then 1 kilowatt for electrical heater is typical at home. So this one has 4 heating coils, and this one use 2.2 kilowatt size. So 6 megawatt for large wind power is a big one, right? Big electricity. Say how many of this electric heater can be used by using? So 3,000 heater can be maintained by 6 megawatt wind power system. So imagine that if you install 6 megawatt large wind power system around Ulleungdo, one of the big island in Korea, then the population inside Ulleung Island can use electricity coming from this wind power system. That is good, right? And gigawatt means 10,000 megawatt. That is our commercial nuclear power plant, right? This one is, see that 1.4 gigawatt, right? 1.4 gigawatt. So approximately 1 gigawatt is the size for commercial nuclear power plant. And wind turbines, small wind turbines, less than 10 kilowatt. It is used for single homes, single farmers can use, right? Remote application, something like water pumping, telecommunication site, and ice making in rural area. And intermediate size is up to 200 kilowatt. Village, hybrid, distributed, and large size can be more, right? And they need to have a central station and also distributed power by using smart grid is needed to distribute electricity. Questions? No?
Professor, I had a question.
Sure, go ahead.
Is it possible to stack wind turbine like one on top of another so that we can increase the capacity?
Oh yeah, theoretically it is possible. The problem is the footing, because wind power can push the system altogether. They can, if you stand inside the high wind, you may turn over yourself because of wind power is higher in the storm area, right? So wind power is using against the wind, right? They facing up the wind, high wind. So pushy power is very big, right? So if the tower is higher and higher, then is as a single beam, right? One-sided beam, then it can be collapsed. So the structurally is unstable. That is one biggest problem. The other one can be the interaction between blade, right? So when there is a wind farm means there are hundreds of wind power system at the one site as an array of wind power system. And behind the one blade, the energy level is going down, right? Slowly going down because we consumes energy. We already used the energy inside the wind. And then after that, behind the wind power system, the power generation level can be lower down, right? So we need to have some distance between location of each wind system. That can be another engineering problem. How far it should be then? Usually we should have a 10 distance of diameter of wind power blade. So 100 meter of in the blade size, then the next wind power system should be 1 kilometer behind, something like that. There is a research on this kind of topic. Good question. Any other? Okay, then we can move, continue. All right. Here is one video, short video. All right, let's see this.
We humans have harnessed the power of wind for agricultural and industrial purposes for centuries. Today, however, wind is used as an affordable, renewable and climate-friendly electricity source. At Ørsted, we build offshore wind farms across the planet to bring green energy to millions of people. But how does it work? Naturally, a wind farm needs wind to generate energy. So we find locations where wind conditions are optimal, water depths are shallow enough for us to fix the turbines to the seabed, and there is enough space to install hundreds of huge turbines. The largest of our turbines have a rotor diameter of over 167 meters and stand 195 meters tall. The sea winds are captured by their giant blades and transformed into energy inside the nacelle. The rotating blades cause the main shaft to rotate, with a gearbox transferring the rotational speed to a high-speed shaft. This turns very rapidly, which allows the generator to generate electricity by spinning a magnet past coils of conductive wire. This process is known as electromagnetism. The electricity generated from all of the turbines in the wind farm is then fed to a single offshore substation, which then transports the energy to shore via high-voltage cables. Once inland, the electricity is transformed at the onshore substation and fed into the public grid, where it is ready to power the lives of millions of people. Since we built the world's first offshore wind farm back in 1991, we've installed more than 1,200 offshore wind turbines. And for every wind farm we build, we're moving one step closer to a world that runs entirely on green energy.
Good. So Ørsted is a place, probably, or company in Denmark. Right? Okay, that's it for the single first lecture. Question? Further question? No, otherwise we can continue on discussion session by Yun-Sang.
Can you see the screen?
Yes.
Today I bring a discussion topic about ocean garbage, because a few weeks ago we did about loop current and we said about 5 gyres, these ocean garbages, and I saw one video about ocean garbage, and I think it is enough to discussion.
The world produces enough plastic each year to build 50 pyramids of Giza. That's over 350 million tons of candy wrappers, PVC pipes, and synthetic t-shirts. While most of it ends up in landfills, 8 million tons of plastic winds up in our oceans each year, where most of it finds its way into massive garbage patches around the world. And the biggest of them all is called the Great Pacific Garbage Patch. If you picked up each piece of plastic in the Great Pacific Garbage Patch, you'd carry away about 1.8 trillion individual pieces. That's 10 times more plastic pieces than there are stars in our Milky Way galaxy. And it would weigh a whopping 80,000 tons, equivalent to the weight of 3 Statues of Liberty. Half of the entire patch is made of plastic fishing nets, lines, and ropes, which come from intense fishing activity near the area. The other half is mostly hard plastics and films, like water bottles and plastic wrap. But don't let the name Great Pacific Garbage Patch fool you. It doesn't look like a giant mountain of trash at all. It's actually scattered over a region of ocean that's twice the size of Texas, according to some estimates. So if you wanted to pick up every piece of plastic, it would take you 121 days at a walking pace of 5 kilometers per hour to cover the entire area. Though in reality, there's no true end, since the garbage patch is constantly ebbing and flowing with the ocean currents. But let's pretend we could scoop it all up into one place. There'd be enough plastic to fill 100 Boeing 747 planes. And the patch is only getting bigger. It's actually been growing exponentially larger for nearly 70 years. Partly because once the plastic is there, it'll stick around for centuries. Those plastic fishing lines, for example, will take 600 years to break down. And even after they break down, the damage doesn't stop there. Most end up as microplastics that are too small to see with the naked eye, but can make it into the bellies of sea animals, and ultimately, the humans that will eat those animals. Worldwide, researchers have found ingested microplastics in every species of sea turtle, nearly 60% of whale species, and almost 60% of seabirds. Plus, more plastic is pouring into the world's oceans each day. In fact, experts estimate that by the year 2050, the amount of plastic in the oceans will outweigh all the world's fish. Think about that the next time you toss your water bottle in the trash because the recycling's full.
Okay, this video was about ocean garbage. And as it mentioned, there are lots of plastic and plastic garbages in Great Pacific Ocean. And most of them consist of plastic fishing nets, lines and ropes, or plastic bottles or plastic wrap. And according to the video, they need long time for breakdown. So today's discussion topic is solution of ocean garbage problem by removing those garbage, because there is so many campaign about preventing the ocean garbage or that kind of thing, but there is few chance to talk about removing. So here is one existing solution. I think it can be one example.
1.8 trillion pieces of plastic float at the surface of the Great Pacific Garbage Patch. Here, the ocean cleanup is deploying the world's first technological solution to this growing problem. The principle behind it is simple. Create a coastline where there are none. Concentrate the plastic and take it out. The system consists of a 600-meter-long floater and a 3-meter deep skirt attached below. The floater provides buoyancy to the system and prevents plastic from flowing over it, while the skirt prevents smaller particles from escaping underneath. As the impenetrable skirt creates a downward flow, marine life can safely pass beneath it. Here is how the system catches plastic. The system takes advantage of 3 natural oceanic forces: winds, waves, and currents. Both the plastic and system are being carried by the current. However, wind and waves propel the system only, as the floater partly sticks above the surface, while plastic is primarily just beneath it. The system thus moves faster than the plastic, allowing the plastic to be captured. The skirt extends deeper in the middle of the system than on the outer edges. As the current applies pressure on the skirt, the system naturally adopts a U shape, which enables it to concentrate plastic in its center, like a funnel. The drag generated by the skirt also acts as a stabilizing force, allowing the system to reorient itself when the wind changes direction. And because the system, like the plastic, is free-floating, it automatically drifts to the areas with the highest plastic concentration. Fitted with solar-powered lights, anti-collision systems, cameras, sensors, and satellite antennas, the system actively communicates its position at all times and continuously gathers performance data. Periodically, a support vessel comes by to take out the concentrated plastic, like a garbage truck of the ocean. The plastic is then transported to land, recycled, and made into durable products. This is the first of a fleet of 60 systems. Once deployed, the fleet is expected to clean up 50% of the Great Pacific Garbage Patch every 5 years.
This is one example, and what I want to discuss is what are the possible solutions of removing those ocean garbage, and what will be the challenging point of cleaning ocean. Like the video says, one of the challenging point is ocean lives, that kinds of thing. So is there any ideas?
I think the solution mentioned in the video is the most appropriate, because in that way we can redirect the garbage in a location where we would want to move the garbage to. And regarding the challenges, big challenge could be, as mentioned, the danger to marine life. And there could also be a danger of it affecting travel route of different ship. If the garbage patch happens to be in a route where major transit occurs. So that's also a point that needs to be taken, and a coordination between different entities needs to take place.
Regarding the ocean garbage, I think the most important thing is to remove the garbage from the ocean as soon as possible. In terms of the policy of government, it might be helpful to legislation the marine cleaning activities on regular basis, or make a compensation about the cleaning activities. And in terms of the technology, using the ROV or AUV technology, it might be helpful to remove the marine garbage at low cost. In addition, if AI technology may be combined to ROV and AUV technology, then more precision for removing the target garbage on specific spot would be possible.
I think that the most challenging point uh, is not is as the this ocean garbage is on the international sea. So I think that none of the country want to give some investment on to remove these garbage. So I think they need international organizations to take a care for this problem. And there's I agree with the Sungmin's ideas that the ROV or AUV can be a solution for removing ocean garbage, and I think that that idea can be also used with the ideas came from the video.
I think another challenge that could be is that there is no way to tell where the garbages are coming from. So like from which country the garbages are coming from. So regarding the cost of operation, it would be difficult to determine who would pay or who shall pay for the cleaning up of the ocean. So I think, as Kian mentioned, an international body would help to mediate the problem, but still, like, the fact remains that even for an international organization, fund needs to come from someplace, and some countries might not be willing to cooperate, and especially if the area happens to be in their own within their own sovereign borders.
Yes. To summary, most of the international organization needs to make some regulation, but there's also some challenging points like the cooperating, and there was some ROV and AUV ideas, and there was also a transporting issue, and this is the only topic what I prepared for discussion. And for conclusion, I saw a very interesting idea to prevent ocean garbage. So let's see and conclude the discussion. It is about making ocean garbage as a nation. That kind of project.
In the Pacific Ocean, there is so much plastic, an area the size of France has formed. Governments have simply ignored it. So we found a way to ensure they couldn't, by turning the country-sized trash patch into an official country.
Les trash isles.
To trash isles.
A la isla de plástico.
Des îles poubelles.
Introducing the Trash Isles. On World Oceans Day, the Plastic Oceans Foundation and LADBIBE submitted an application to the United Nations to recognise the Trash Isles as an official country, because under the laws of the UN, other countries are then obliged to clean it up.
Declared the part of the ocean where all the trash is gathered, the plastic, the trash isles. Has the petition been received, and what's your take on it?
I think it's a very innovative and creative way to bring attention to a problem that is often not seen.
Having met the criteria to become a country, the Trash Isles began recruiting citizens online. In the first few weeks, we had more citizens than some countries. The Trash Isles had everything an official country needs: a currency called debris, a passport for new citizens, and a national flag. We even had big-name celebrities signing up.
I think this is the first honorary citizenship I've had from any emerging nation.
Thank you very much.
Trash Isles citizenship.
Trash Isles.
Trash Isles.
Some even took on official roles.
I'm Judi Dench, the Trash House Queen.
I will be the best Secretary of your Defense that I can.
With over 200,000 citizens, 50 million video views, and 500 million people reached, the Trash Isles put the plastic problem firmly on the map.
I will make reference to the Trash Isles from here on out.
Okay, thank you for participating.
Very nice. Right. I remember that in about 2 or 3 years ago, in the same class, there was a term project, which is about this topic. And I remember that one team proposed a floating plant at the site, something like a FPSO, the ocean plant that is floating and located at the trash. And there they collect plastic garbage and then processing them, because as a plant, and provide some good material of them, including energy too. Some probably they may need to classify and collect some utilizable, good, reusable part, recycling, so they can produce a new plastic out of them. And the others can be burnt out and can be used as an energy source. So that was another project at that time. Anyway, good topic there. Right. Okay, so 25 minutes left, so we can continue on next material, class material. So because we have a catch-up class for delay next Tuesday, so we can be slowed down for the schedule. So don't worry. So this is the second part. I may not, or may finish up this one. So we move on to tidal energy and wave energy. All right, so tidal energy, it is a special area. You need to map area is important. So there we can have a concentration of tidal energy, something like a base open to one direction and all straight, connecting two seas, and also tune of resonance is effective. So in the picture, left-hand side, it looks like England, southwest corner of England, southern estuary, right? And then you see that it Bay Area.
Excuse me, Professor, I cannot see the PPT slide.
Oh, sorry. I should have a 화면 공유, right? Sharing the screen. Thank you. Right. Now you can see this, right? So the picture left-hand side, bottom is southwest corner of England, where the Bay Area is very deep. And you see that the height of tidal rise, Cardiff and is one city at that area. And so using this kind of high tide level, you can use that tidal current water is moving, so they can be utilized. The other one is on right hand side. There is a strait, and tide is fast in the bottleneck. But this one is very famous in Korea, something like Ultolbok, because of the General Isunshin. And so this one is good in that you can have a predictable power output. So, every 6 hours, there are two return of coming tide and returning tide, and twice per day. So it's a energy level can be predictable. Comparing to the wind, wind is not predictable. That is the disadvantage of wind power system. Right? Only when the wind is high, the power is generated. So that is the fluctuation, unpredictable energy level. And tide is coming from movement of sun and moon. Especially the moon is the main influence to the water movement. So we call this is a lunar tide, and also there is a small percentage of solar tide. But when they are in the straight line together, sun and moon, then it can be the highest peak, right? So there is a name called the nip tide, and the other one is, what is the name? I can't remember this. Spring tide, right? Spring tide and nip tide, right? And then, so in the bottom picture, you see that tidal height is 24 hours. There is a two cycles, right? High tide and low tide. So tide is a periodic rising and falling of water that result from gravitational attraction of the moon and sun. And solar tide force is about half of the lunar tide, because the lunar is smaller, but it's closer to the Earth. And this is a flow tide, ebb tide, or spring tide, and that is spring and nip is not every day, right? It is every once a month, right? Because moon is rotating 1 month. But this one is for every day, flow tide and ebb tide. So water is flowing down and up. So this one is picture coming from France. It's a tidal power plant. So cycle is 12 hours, as we see. And there is a bridge, truck is coming, but water is flowing at the bottom of the dam, right? When the tidal difference is used. So once the water is inside the dam, then after ocean level is low, then we can also generate using turbine generator unit. So two-way power generation. So it is cyclic and also periodical and predictable energy. So tidal energy capturing, usually we use a dam. So we use a potential energy of height of the water level and change them into kinetic energy. The other one is a tidal stream capture. There is no dam, only tower inside the water. So the turbine and oscillating wings and other things are used. So without them, there is also still tidal current used for the power generation, especially near the Taiwan island nation. The current is very high near the Kuroshio current is higher near the Taiwan area. So there is a project inside Taiwan to produce tidal energy. Looks like a picture on the bottom of this figure. Okay, then the tidal barrage, the dam, we can calculate using equation, right? So flood and ebb phases, and then there is a power generation depending on flow rate and water density, gravitational acceleration. Head is height of the water and efficiency there. Right? So something is the same. We can have a YouTube video here.
Tidal power. Tidal power is a form of hydropower that converts the energy from the natural rise and fall of the tides into electricity. Tides are caused by the combined effects of gravitational forces exerted by the moon, the sun, and the rotation of the earth. Tidal plants can only be installed along coastlines. Coastlines often experience 2 high tides and 2 low tides on a daily basis. The difference in water levels must be at least 5 meters high to produce electricity. Tidal electricity can be created from several technologies, the main ones being tidal barrages, tidal fences, and tidal turbines. Tidal barrages are the most efficient tidal energy sources. A tidal barrage is a dam that utilizes the potential energy generated by the change in height between high and low tides. This energy turns a turbine or compresses air, which in turn creates electricity. Tidal fences are turbines that operate like giant turnstiles, whereas tidal turbines are similar to wind turbines, only underwater. In both cases, electricity is generated when the mechanical energy of tidal currents turns turbines connected to a generator. The generator produces electricity. Ocean currents generate relatively more energy than air currents because ocean water is 832 times more dense than air and therefore applies greater force on the turbines. Tidal power is easy to install and renewable, having no direct greenhouse gas emissions and a low environmental impact. Because the ocean's tidal patterns are well understood, tidal energy is a very predictable energy source, making it highly attractive for electrical grid management. This sets it apart from other renewables that can be more unpredictable. However, adoption of tidal technologies has been slow, and so far the amount of power generated using tidal power plants is very small. This is due largely to the very specific site requirements necessary to produce tidal electricity. Additionally, tide cycles do not always match the daily consumption patterns of electricity and therefore do not provide sufficient capacity to satisfy demand. That's tidal power.
Okay, any questions?
Professor, I have a
Question? Okay, go ahead.
What's the difference between tidal energy and wave energy, like ocean wave energy? Are they the same?
You need to know what is the difference between tide and wave, right? Waves on the surface. Actually, there is also an internal wave too, but usually we see the waves on the surface of the ocean. Tidal is a movement of water in one direction. So larger scale. Kuroshio current, can you remember the Kuroshio current? That is starting from around Philippine area toward Taiwan and then into the between Korea and Japan. Right? So it's a circulation at the whole Pacific Ocean, something like that. There's a current.
But there
go ahead.
So there are only a fixed number of tides in a day, right? So wouldn't that make tidal energy less efficient in generating energy?
It depends. Anyway, let me continue. The wave is generated by the wind, right? And tide is generated by the Earth and Moon motion, rotation. So energy source is a little bit different. And also the phenomena of water movement is a little bit different. That's why we divide into just movement of water. So tidal current and also earth current is two different types of to think about the energy density. As I told you before on time. So in the video, they are saying the density of water is 130 times larger than what air. So that water current tidal power blade is turbine is much higher chance of generating energy than wind. The problem is the energy density per cubic, say, square cubic meter of air or wind or current. So speed of the current and speed of the wind and density together. So the equation is saying all together, but in terms of physical analogy, you should think about the energy density per area of square area or per cubic solid of water or air. But depending on the time scale, they have a different speed of current and speed of wind. All right, thank you very much. We will see a little bit more in the later stage, because the wave is coming in the next section or on Thursday. Right, so you can raise further the question at the time too. Right, this is a tidal power dam, different location. First one is in France, second one is Canada, third one is China, and fourth is Korea. And spring tide, the height is biggest in France, right? 13 meters. The difference is good, right? And capacity is the size of the dam or water reservoir, right? So it's also, the capacity is larger in Shihwa in Korea, right? Very big. And construction year is very new to Shihwa, right? The other ones is 50 years ago. Right? And annual power output is depending on the capacity. And generation type, it can be the turbine type, double effect turbine blade or single effect. Okay, and then
Professor, your screen is not shared.
Sorry. Continuing the, sorry. All right. All right. Thank you for commenting on this. So this is a comparison of tidal power dams. In one France is big, and then the fourth one in Shihwa is a Korean one. They have a similar size. The year is very, France one is very old, 50 years ago, but Shihwa is only 10 years old. The other thing is depending on the size. Gate is also depending on the capacity. Right. And this is a lake, Shihwa. The picture is coming from tidal power project of Korea. Opened in 2011, 10 years ago. There are 10 generators, 25 megawatt. So you see that the wind power system is grow into 20 megawatts now per single system. So comparing to the size of this dam and lake, you may see that wind power system goes very big nowadays. And Garorin Bay, there is another project, but it was canceled at the time. But in the future, it can be revived again. Right? Right hand side, there's a table of numbers, tidal range, and barrage length. Length of the dam is 13 kilometers, very big one, right? And bay area is 43 square kilometer. Okay, construction cost is there. And this is a straight type tidal place. Ultolmok is famous for Korean people because of General Isun신. And between Korean Peninsula and the island, at the left bottom side, there is a map of Korea, small map, and the island of Jindo is located here. And between the island, left-hand side and right-hand side is a peninsula. There is short, a narrow strait, so that tidal current is very high speed, twice or 4 times per day. So there is a pilot plant and commercial plant, and the others are in the picture. Okay, and so there are ships are coming back and forth, and also the current speed is very high, so that there is also high wave is showing. So you need to have a very careful on blocking or colliding with the ships to this facility. Okay, there is another idea called, we are moving on to wave energy now. Okay. So wave energy at the ocean surface only. Wave is showing here. There is also internal wave in the later stage, but that is not used for wave generation, energy generation. So Pelamis looks like this snake on the surface. And when the wave is up and down, then the whole body is moving up and down together. So that it looks like a snake moving. So by utilizing this movement, you can generate electricity. Let's see the video. Oh, how can I capture this video? This way. No sound there. Right. The Pelamis wave energy converter. Sea snake. Hinge joint and cylindrical tube section. So cylindrical pumping. Hydraulic rams. So there is a flow of liquid that generates energy. Okay, there's the idea. Right. Also, I guess there is another video. Let's see what is inside. Good. Question? Otherwise, we can stop it at this point because the time is up. So we can continue later slide on Thursday. Question? No question. Also on Thursday evening, we have a class, right? At that time, the TA Jihu will show you a small experimental for your fun. We'll see the experiment, small experimental device. All right, that's it for today. See you on Thursday. Bye now.